Hello and welcome to this video. This is the third part in this series that we're talking about FSMs, finite state machines, and specifically we're trying to create a finite state machine. The essence of this finite state machine is simply to have a, the essence of this program is to teach finite state machines, but the particular machine we're coming up with, FSM1, in FSM1, our clock FSM is the actual finite state machine within it. It's in there as a component. Then we have a ring counter that's connected to the LED lights of a DE10-Lite board, and the idea will be to get the lights moving with a certain frequency. So the FSM, in this case, the clock FSM, divides the frequency and gives us the specific frequency we are interested in, depending on the frequency, depending on the state of this clock FSM. And then once this clock signal comes into the ring counter controls the lights. So here we want to have our top level entity FSM1, and really all we have in here is just interconnecting the components together, and that should be just about it. So let's go ahead and write the code for FSM1. So we declared this earlier on 2 videos ago. Let's now populate it. So ports, I believe there were 3 input ports and 1 output port. Let's just confirm that. So we have 3 input ports, each one of them of type standard logic, 1 output port, LEDR. So let's go ahead and encode that. So we have button as our input port, we have clock as the input port, and we have, what's the third one? Reset as the input port. These are all input ports of type standard logic. And then there is 1 output port that is LEDR. Again, I said I'm being lazy here because in my QSF file I'll have very little to do if I use this in uppercase this way. Standard logic, vector, 9 down to 0, because it's 10-bit output. Okay, no semicolon out there. We shouldn't need the numeric standard for this. Okay, so I could go ahead and do things, but usually I like to have a signal for every connection I'm going to have in there. Is it actually absolutely necessary? No, but well, I just prefer connecting things to signals. That way I know for sure what is going on where. So I have S underscore BTN, S underscore CLK, S underscore RST, and I'll have S underscore CLK out, because CLK out. So in reality, I should label all of those in this diagram. So what I'm just simply doing is I'm calling this S underscore BTN, S underscore RST, S underscore CLK. Then this signal interconnecting these things, I'll call it S underscore CLK out. Okay, that is probably not legible at all. And then we'll have this output here, S underscore LEDR. So this will be S underscore LEDR. My sincere apologies. I know my writing in here is terrible right now, but well, yeah. Okay, so we have these all of the same type, standard logic. And then we have our S underscore LEDR. I'll just keep this as lowercase here to save myself some trouble. Of type standard logic, vector, 9 down to 0. Good, so these are here. Next, we have our port mapping to do. So let's say I want to map, there are 2 entities I want to map clock FSM. So let's say CLK FSM. That's the first port map I want to do. Then let me see, I want to have work.clk FSM. The name of the architecture was what? Name of the architecture, divide, and this one is count. Okay, so divide, and I'm going to do a port map. That will be in here. I'll come back to that in a minute. And then ring, okay, so CNC. I'll say M underscore ring counter, and this will be work dot ring counter, and it was count port map. Good. So this here, now let's go ahead and do our mappings. And here we have button clock resets, button clock reset clock out. So button Button gets mapped to S underscore button. Clock gets mapped to S underscore clock. Give myself some space over here. Reset will get mapped to S underscore reset, and clock out will get mapped to, and I'll just give myself a little more space on this side, S underscore clock out. I believe those names are correct. Yes, those names look correct to me. So that's that for that. Let's go to ring counter. Ring counter is 1 in, okay, 2 in, 1 out. It's clock, reset, and counts. So clock, CLK gets mapped to the same input. The input of this, yes, same input as CLK. Reset gets mapped to the same inputs. S underscore RST. Give myself some more space. And then my output, what's called CNT, gets mapped to S underscore CLK underscore out. So let's just confirm that. So this is a, nope, this is a, oh, sorry, that is that. Oh, so sorry about that. So I've done this wrong. So this clock is not S underscore clock. The input to ring counter, the output of ring counter was that. So this will now be the input to the ring counter. So clock is mapped to S underscore that. I'll move this to the next line so that everyone can see what I'm typing there. And then I'll bring this to this line here. Okay, so the count CNT as the out will go to S underscore LEDR. Okay, so with that sorted out, I need to do my hardware connections. Or, well, not hardware connection, I'll connect my signals. Okay, so BTN is, no, SBTN is connected, receives its inputs from BTN. S underscore RST will receive its input from RST. Then my S underscore CLK will receive its input from CLK, and the output LEDR will receive its signal from S underscore LEDR. Okay, so I think with that we are done. If I'm correct, we are done. Next, we need to get the QSF file, and we need to update the QSF file, and once that is updated, then I think we should be good. So what am I looking for? FSM1 and QSF file. So take my QSF file, edit the QSF file here, and I'll look for master QSF file, which I have saved somewhere on the pick the clock. Pick clock, I need a clock. Copy, paste that in here at the bottom. Why not? At the bottom, and I'm going to use not the ADC clock, I'll use this first one. Nope. I'm going to use this. So change this to CLK. And that's good. Clock done. Next, I want to go to buttons. Buttons, 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 buttons. So key and LED. I need this to copy and back to FSM1. Paste here. So LEDR is perfect as is. I gave it that name so I don't have to worry about it. I'll use my key 0 as my reset, and then I will use my key 1 as my button. So change this to 1 as my button. Replace all. 2 instances replace. Good. And I think we're done with this. Let me go ahead and compile this project. So just to recap, this is our top level entity. All I have here really is a structural definition of the architecture. The work is being done in the various components. This component here, clock FSM. Okay, so there's an error. Let me come here and check this. So S underscore begin statement is needed. Oh, so sorry. I did not give it the name signal. So it was wondering why I did not have a begin signal. Someday I'll write VHDL code and it will have 0 errors in it the very first time. And I'll probably make a video about it. Okay, so in our top level entity, FSM1, it has 2 components, clock FSM and ring counter. Clock FSM takes in the input clock and divides it. So clock out is the clock that is divided. The value of this is dependent on the states. Another error to check. So I have left something out, maybe a semicolon. What did it say? Looking for something near resets. Okay, so let's check this. Yes, I left out a comma there. Okay, and compile design once again. So this does division. The output of clock FSM is S underscore clock out. That S underscore clock out is sent into the ring counter, and the ring counter does its counting based on that. Another error to deal with. LED, LERD. So it should be LEDR, LEDR. Learn to spell. Compile. So the ring counter does its counting in a ring, and the output of the ring counter is sent directly to the LEDs. So if this compiles all the way through, then we can go ahead and test our code and see that it runs. Yay, no syntax error. Okay, so now fitter and placer. Hopefully we should have no issues with that. If it helps with your confidence, usually I don't have any issues with the fitter and placer, even though there is one scenario we could possibly have, but then it won't happen. Well, at least not in this code. So we shouldn't have any issues with this. Then we have our assembler and timing analysis, and we should be able to program this onto the board and test this. So good, it is done programming. Program device. And I'll tell it to go ahead and program the device. So what I'll do is so once I program the device, I'll pull up my webcam. Do apologize, I don't have a memory. I don't have a what's it called? I don't have a good camera here, so the camera of this is quite faulty. So I hope this shows up well. Okay, so sorry, programming it again. And then pull up my webcam, and this is the board. Apologize, lighting is not the best over here. Now we see that apparently some counting is going on, but something is wrong with something. Clearly something is wrong with something. Let's see if reset is working. Key 0, I press it. Key 0 is reset is definitely working, but once I release the reset, things are going kind of it kind of looks haywire to me. Okay, looks like things are not going quite like they should. So what is going on? Let us come back to our code over here. Now, the clock FSM is probably where we need to check things. And yes, clock FSM is what we need to check. And first of all, there is one big issue. We checked if button is 1. And button is always 1, more or less. So it is just transiting from state to state to state to state to state to state. And so now let's go ahead and recompile this. So if I have to recompile a couple of times, I think I'll just try to in post decide to speed this part of the video up so that you don't have to wait through all the entire compilation procedures. Good, it's done compiling. I'll pull up my webcam once again, and then I will open up the programmer so that, well, hopefully you can see this while I program it. So go ahead, start. Programming, it's done. And here we see it is working like we expect. So remember, there's a reset state, and then it has probably gone into state 1, very likely gone into state 1. And now it just simply will stay in this state. There's a frequency with which the LEDs are moving. So let's bring the webcam up to the front. So there's a frequency with which the LEDs are moving. Now I'm going to go ahead and press reset to see if everything is fine. Reset, everything goes, release it, and it's still fine. It remains at that frequency it was at. Now I'll go ahead and press button 1 because that should make it transition to the next state. So it should become twice as fast. Okay, so let's try that. Now, so is this twice as fast? This is not twice as fast as the previous one. This is not, I mean, it's supposed to have just 3 different states. So this looks like what the state we were in just now. So clearly it's like it's going to a state, but we can't guarantee what state we go to. And to give you a hint as to why that is, if I hold down the button now, You see that it is just transiting from state to state. This way it looked earlier on. And that's the problem I alluded to earlier on that we will definitely have. So we are not to check when button is 1 or when button is 0 now. We are not to check when button is 0. Rather, we're supposed to check something else. So we're supposed to check rising edge or falling edge. That is what will work. So let's go back into our code. Let's go back into the code. Clock FSM is where the problem is. So here we're checking if button is 1, but we want to check rising edge. So instead, I'm going to do something. I'm going to come up here, and before we start the case structure at all, I'm going to check that rising edge. So once again, another thing that I should have done is I should have checked for reset also within the state. And the reason is this. Sorry, just give me a moment to... Okay, let me just pause here and I'll continue from here. The reason why I should check the reset state is if my present state is, say, 1, 0, next state is supposed to be 1, 1. At this point in time, if my present state is 1, 0, it means the last next state I had was 1, 0. Okay, so next state is 1, 0, present state is 1, 0. So we're in this particular state. Button has not yet, we've not gotten an active clock transition, or the button has not made a transition to the next state. If I press reset over here, then reset will make the present state 0, but at the next rising edge of the clock, next state will get assigned to present state. What is next state? Next state was 1, 0. So if I was in this state when reset was pressed, by default, after resetting to 0, it will bring me back to this state that I was in previously. And that is not quite what we want. So we want a case that whenever we reset, our next state will also get overwritten. Okay, so next state, if we want, we can set this to 0, 1 if we want, but it really doesn't matter. If we set our next state to 0, 0 or 0, 1, it's fine. Because for this particular, so let me set it to 0, 0, because that's a good, well, I'll set it to 0, 1 actually. Because I know that my code, okay, I'll set it to 0, 0. So set it to 0, 0, so that once that happens, it will definitely bring me into this state and definitely stay in this state. Then this state now tells me what to do next. Okay, so having done that, then next thing I will do is now check for, I could check for the falling edge, but I'll check for the rising edge of the button. Now, by checking for rising edge of the button, it means when I depress the button, nothing happens. But when I release the button, then it will enter this case and check this case. So I'll just indent this, not because the indentation matters, but because for my reading, it will be easier to read if I'm reading that. And now I don't need to check if this is equal to 0 because this actually is useless to me. So now it just turns out because I'm checking for rising edge, I can take one of these off just to make the stuff line up. So now on rising edge, it will simply, it will definitely transition in each state, okay? Rising edge of the button, it will definitely transition in each state. Okay, so definitely transition in the state. Now, there's just one challenge we'll have with this, and this is the fact that we have this state in here. Okay, so this is supposed to transition definitely no matter what. Okay, this is supposed to transition no matter what. However, because it is going to wait for the rising edge of the button, it's going to require me to press the button before this will happen, and that will be a bother. So I'll go ahead and make my next state 1, yeah, 01, so that without pressing my button, even if I'm in present state 01, this over here will force it to go into state 1 whenever I reset. So I think I'm good with this now. I'll go ahead and compile this program. And so now when we're done compiling this and when we do program, this time it should work the way we expect it to work. Fingers crossed. No syntax errors, that's good. Place and route will definitely run through because we didn't have an error with that. We didn't change much in terms of, well, it could fail in the sense that we've changed the logic, but we've not added that much. So check the resources that are being used. We're just using 58 logic elements out of 49,760. So we're about ready to program. I'll pull this to one side. I'll pull up the webcam and we'll go ahead and start this. Done programming. Once again, the frequency of this is as is. Reset button still does exactly what we expect it to do. Sorry. Okay, reset button still does exactly what we expect. Now button 1. Depress, nothing happens. Release, frequency is doubled. Press, nothing happens. Release, frequency is doubled again. Press, nothing happens. Release, it should go back to that first frequency. That's what happens. Okay, so now we can just, dependent on the state, we can change the frequency depending on the state. Okay, so that is working just like we expect it to. Reset once again. I press once and it takes me into the second state. I hope we get that. So this is working the way we expect it to. Just one last thing I want to do in this video, and that is just to show what happens, how Quartus does run things. So if we go under analysis and synthesis, if I make this drop down under netlist viewers, if you come here, you can have the RTL viewer. RTL viewer shows the register transfer layer. Yes, go ahead. So it shows you the RTL layer and shows you what things look like within it. So this was one component, this is another component. You see the big plus sign which says you can expand this. Let me first expand the counter. Expand the counter, and this is what happens within the counter. And this makes sense because we use if, else if, else if, else if, else if. So for every of the else ifs, you have this nested system over here. Minus, so that brings that here. And then I have this plus. And this is what happens within the clock FSM. A number of registers like we expect in any FSM, a number of multiplexers, again, like we expect in any FSM. Okay, so this is typically what an FSM looks like, and then we have some combinational logic in there. That'll be it for this video, and hope to see you in the next one.